In the crucible of the Cold War, the battle for technological supremacy between the United States and the Soviet Union
escalated from the terrestrial
to the terrestrial, to the celestial.
The space race was not merely a contest for orbital prestige.
It was a critical pursuit of data, knowledge, and strategic dominance in the new, uncharted frontier of aerospace.
This pursuit demanded more than just powerful rockets.
It required a new class of experimental aircraft capable of reaching the very edge of space,
pushing the boundaries of velocity, altitude, and human understanding. But ahead lay two far more formidable obstacles: the thermal barrier of hypersonic flight. It was into this daunting chasm of the unknown that the North American X-15 was conceived. First proposed in the 1950s, the X-15 was a quantum leap in aviation philosophy. While its predecessor, the Bell X-2, had impressively achieved Mach 3.2.
The X-15 was designed to shatter that record.
Targeting the hypersonic regime and an altitude beyond the Kármán line.
It is the 100-kilometer boundary that technically defines the beginning of space.
The program's core objective was not to set records, though it would do so in spectacular fashion,
but to function as a flying laboratory. NASA faced a critical void in its knowledge.
How would a craft behave when its control surfaces ceased to grip air and it needed to rely on thrusters? What materials could withstand the plasma-hot temperatures of atmospheric re-entry, temperatures that would melt conventional airframes?
How could a human pilot function and survive in this violent, alien environment?
The X-15 was the instrument built to answer these questions.
It was, in effect, the world's first piloted spaceplane, an essential stepping stone.
That would lay the technological groundwork for the Mercury, Gemini, and Apollo programs, as well as the future space shuttle and the SR-71 Blackbird.
This is the story of its radical, boundary-defining engineering. The X-15 would be flying far too high and fast for an engine to ingest oxygen from the atmosphere. The solution, therefore, had to be rocket propulsion. The engineers required an engine of unprecedented capability. It needed to generate approximately 240 kilonewtons of thrust,
Yet also be compact enough to fit within the plane's narrow fuselage.
The greatest challenge, however, was control. Previous rocket planes, like the Bell X-1, achieved variable power by simply igniting or extinguishing a bank of separate combustion chambers, providing a stepped, all-or-nothing output.
This was unsuitable for a research vehicle.
The X-15's pilots needed a true throttle, the ability to modulate thrust with finesse to probe different flight regimes. Developing this engine, the reaction motor's XLR-99, became one of the program's most significant hurdles. The key to its revolutionary throttleable power lay in its turbopump.
This single device was a masterpiece of engineering, responsible for forcing 8
Into the combustion chamber at an astonishing rate.
Enough to drain its entire load in just 85 seconds. To achieve variable thrust,
engineers devised a way to control the speed of this turbopump. This pump, in turn, required its own power source.
Using the main rocket fuel was not an option. The combustion products were far too hot for a spinning turbine to withstand.
The solution was as elegant as it was potent: a separate monopropellant system.
The X-15's turbopump was powered by 90% concentration hydrogen peroxide. When this fluid was passed over a silver screen catalyst, it decomposed in a violent exothermic reaction, and instantly flashing into 737 degrees Celsius superheated steam and oxygen. This gas jet spun the turbine, and by precisely metering the flow of HO with control valves,
The pilot could directly control the turbopump's speed and thus the engine's thrust. This system was a model of integration, as similar hydrogen peroxide systems were also used to drive the plane's 2 auxiliary power units,
as well as the reaction control system thrusters on the nose and wingtips, which allowed the pilot to steer the craft in the vacuum of space.
The choice of propellants for the XLR-99 was a fraught exercise in balancing power, safety, and thermodynamics.
The primary metric for a rocket's efficiency is its specific impulse,
which describes how much thrust is generated per unit of propellant mass expelled over time.
A liquid hydrogen and liquid oxygen combination offered the highest theoretical ISP due to hydrogen's extremely low molecular weight.
However, in the 1950s, LHG was a logistical nightmare. Its cryogenic boiling point of -2
and its tiny molecules could seep through the microscopic grain of solid metal.
It was not yet a practical fuel for an operational aircraft.
Kerosene, the RP-1 fuel that would later power the Merlin and Saturn V engines, offered a better balance of density and impulse,
but presented its own problems. When used as a coolant, the kerosene of the era had a tendency to polymerize, or coke,
leaving clumps of impurities in the cooling tubes.
That would lead to blockages and catastrophic engine failure.
Hydrazine, while potent, was notoriously unstable and prone to explosive decomposition when used in regenerative cooling systems.
The engineers eventually selected anhydrous ammonia.
With an ISP of 293 seconds, it was a powerful fuel.
But its true genius was its thermal properties. To survive the extreme temperatures of its own combustion,
the XLR-99 engine relied on regenerative cooling. It's a process where the fuel is pumped through tubes surrounding the combustion chamber and nozzle before it is burned, using the fuel itself as a coolant.
Ammonia is a phenomenal cooling fluid. It could absorb a massive amount of heat energy from the engine bell without boiling, keeping the metal from melting.
This benefit came at a high price. Ammonia is highly toxic and relentlessly corrosive, attacking metals like copper,
which led to an ongoing battle with failing gauges and seals throughout the program.
it was a dangerous, high-maintenance choice, but it was the only one that made the XLR-99's sustained power possible.
At the altitudes and speeds the X-15 would encounter, traditional aerodynamics textbooks were left at the door.
At Mach 6, air ceases to behave as a fluid. It becomes a compressible, reactive medium.
The design of the X-15 required a completely fresh approach.
A fierce debate raged at the Enaka Ames research facility.
Led by engineer Julian Allen.
Who proposed a radical, counterintuitive idea: the blunt body.
Conventional wisdom demanded sharp, pointed noses to pierce the air and reduce drag.
Allen argued that at hypersonic speeds, a blunt nose would create a powerful bow shock wave.
This shock wave would stand off from the vehicle's skin, creating a boundary layer that would dissipate the majority of the intense frictional heat.
Harmlessly into the atmosphere,
keeping it away from the aircraft structure. This theory was proven correct and was incorporated into the X-15's nose and wing leading edges, and would later become the foundational principle for all atmospheric re-entry vehicles, including the Apollo capsules.
The plane's re-entry profile, a high angle of attack approach to bleed-off speed, created another unique aerodynamic challenge.
At an angle of attack of 20 degrees, the massive fuselage would shield the upper vertical tail,
rendering it completely useless for yaw stability.
Conversely, the lower tail fin would dip into the high-pressure zone under the wing, making its effectiveness critical.
This lower fin was therefore made exceptionally large.
This, however, created new, more mundane problem. The fin was so large that the plane could not land on its short skid landing gear
without it striking the ground.
The solution was blunt and pragmatic. The pilot had to jettison the lower section of the ventral tail before landing,
allowing it to parachute back to Earth for recovery and reuse.
Perhaps the most distinctive feature of the X-15 was the primitive-looking, wedge-shaped profile of its vertical tail. This design was, bizarrely, rooted in Newtonian-era physics. While complex modern aerofoils failed at hypersonic speeds, the simple wedge shape generated predictable pressure and stability. Its behavior closely approximating Newton's 17th century equations for particle impact.
This shape, while creating significant drag at lower speeds, was a perfect stabilizer in the hypersonic regime,
and was even fitted with extendable speed brakes to aid in deceleration.
The primary challenge of hypersonic flight is not speed, but heat.
The SR-71, flying at Mach 3, saw its titanium skin heat to over 300 degrees Celsius.
The X-15, pushing past Mach 6, would face temperatures exceeding 1,000 degrees Celsius.
This is not merely hot. It is a plasma environment where the air itself becomes a superheated, chemically reactive sheath.
Titanium was insufficient.
The solution was a nickel-chromium superalloy called Inconel X.
This wonder metal was one of the few materials on Earth that could not only survive such temperatures, but, critically, maintain its tensile strength while glowing red hot.
Where aluminum and titanium would turn to putty, Inconel X held strong.
This strength came at a severe penalty. An Inconel X airframe was estimated to be 180% heavier than an equivalent aluminum structure.
A massive burden for a rocket-powered plane.
Furthermore, the material's thermal properties created a host of secondary problems.
During one Mach 6 flight, the non-uniform thermal expansion of the plane's structure caused an Inconel window frame to buckle,
shattering the outer quartz pane mid-flight.
The pilot miraculously survived. The engineers also discovered that shock waves and turbulent flow, often tripped by tiny gaps or seams in the plane's skin, could create unpredictable hotspots of extreme local heating. To hunt down these hotspots, the designers coated the plane in special heat-sensitive paint
that would change color at specific temperatures.
Returning from each flight with a multicolored map of its own thermal ordeal.
These paint maps allowed engineers to identify and mitigate turbulent zones,
such as those caused by expansion joints, by installing small buffer strips.
For the program's fastest flights, even the robust Inconel X was not enough. To survive the push to Mach 6.7, the plane required a sacrificial, or ablative, material.
Which were designed to char, burn, and fall away, carrying the extreme heat with them.
This development was fraught with problems. Some ablative compounds failed to bond with the Inconel X skin,
peeling off when the underlying metal expanded.
An even more bizarre problem arose when one ablative, after burning away from the nose,
began to coat the pilot's windows, rendering him blind.
Oh God, we're blind! I can't see!
The solution was a primitive but effective mechanical eyelid for the left window, which remained closed during the high heat portion of the flight.
The final ablative chosen, a pink material called MA35S, was sprayed onto the plane and in various thicknesses.
It worked, but it had a terrifying drawback. When mixed with liquid oxygen, it became highly explosive,
capable of being detonating by a simple impact.
This was a horrifying risk, given that the plane's oxidizer was LOX, and minor spills during fueling were common.
A white sealant coat was applied to isolate the materials, a thin barrier against potential disaster.
He ignited the engine, and with the help of 2 external fuel tanks, and pushed the plane to the unbroken crewed flight record of Mach 6.7.
The plane survived, but just barely. It landed with parts of its skin melted and scorched, damaged beyond repair.
Point provided the most valuable aerospace data ever gathered.
This hard-won knowledge on rocket engines, hypersonic stability, reaction controls, and ablative materials.
Liftoff flowed directly into the Mercury, Gemini, and Apollo programs.
Experience that could only have been gained from the X-15.